welcome to the session. So in the last class we have been discussing about the Pelton turbine, and I remember that we have done designing of Pelton wheel, and we have even solved some question related to this Pelton turbine, and I've done some explanation on it as well. So before we start with the other session, let me not forget to tell you guys, please try to solve this homework question which is related to Pelton turbine. And with that we will be moving to the next part, which is about the reaction turbine. So before we start about the reaction turbine, let's talk about the wheel, the prayer wheel, which use the running water to rotate it, right? If we just observe this prayer wheel, then we can see that it's using a running water, which causes a kinetic energy. And if you talk about the reaction turbine is basically the upgrade version of this wheel, where it involves it will be using the casing to let the water to enter inside it, right? So the casing they will be using in case of the reaction turbine is the gradually where the area will be gradually decreasing. That means it by the time it's reached at the internal part, the surface area will be very small. So therefore we can say that it's used to increase the pressure. And in case of reaction turbine, along with the kinetic energy, it will also have some pressure energy as well. So basically reaction turbine will contain two types of energy, and other thing is the casing and the runner will always be full of water when it's functioning. And the other thing is, once the water is taken out of the Pelton penstock of this the turbine, the penstock that we use to take the water from the dam, so it will be taken into the casing, which is airtight casing. And now about the radial flow reaction turbine. So there will be of two types, that is inward reaction flow turbine and outward reaction flow turbine. In case of inward reaction flow turbine, this could be the best example, where the water is made to flow from the outside part into the inside part, and this is known as inward flow radial flow turbine. Whereas for the outlet radial flow turbine, it's just opposite of inlet radial flow turbine. The next part is we will be talking about the main parts of the reaction turbine, and the first one is casing. As mentioned in the earlier section, the casing and the runner will be full of water when it's in the running condition. And the moment water is taken out from the penstock, so let's assume this as a penstock, it will be entering into this casing, which means the water will be in the close region throughout the journey. So we can say that the penstock, the casing is made it in such a way that it is a spiral shape, in which the area of the cross section of the casing keep on decreasing gradually, and when it's reached to almost at the end of this circular section over here, it will have the smallest surface area. And with this we can say that with this casing, they are trying to maintain the constant velocity throughout the circumference of the runner. And basically runner blade is made up of the casing is made up of cast steel, and it may other name would be like the plate steel. The next thing is we will be talking about the kite mechanism, and about the kite mechanism they have represented it as kite wheel in this section or in this figure. So the kite van other name could be Kizainon. So the next part is we will be talking about the kite mechanism, and in this figure it is represented as kite wheel. So the kite, and other name could be also known as kite van. And it is usually placed inside the spiral casing or outside the runner blade. And the reason why it is being placed it in such a way is to make sure that when the water running from this spiral casing enter into the runner blade, it doesn't experience any shock. Which means with the help of this kite van, which is like the stationary circular wheel, it will make sure we can change the amount of water that is falling onto the runner blade. The next one is we will be talking about the runner. So in case of reaction turbine, the runner are usually made up of stainless steel, or it's made up of cast iron or cast steel. And the runner, which is like the circular wheel, and it consists of series of radial curve vane. And the reason why they are made it in such a way is to make sure that the amount of water that is entering into the runner, or the water that is leaving the runner, leave without experiencing any shock. And additionally, they make sure the runner vane is so smooth. And the other thing is they are keyed to the shaft of this runner, the one which is shown here. The next one is we will be talking about the draft tube. Before we talk about the draft tube, let's talk about the water that is taken into an enclosed region, where it was in an enclosed surface area when it's in the penstock, then the casing, and then it will be entering into the guide vane, and then to the runner plate. And after reaching the surface of the runner, then basically the work of the water has been done. So it is entering in a radial direction, but when it leaves this runner, it will be leaving in a axial direction. However, the amount of water that is containing inside this runner blade, the pressure may not be equal to the atmospheric pressure, which means, like, if you see in this figure, that the amount of water around this region may not be equal to the atmospheric pressure. So in order to make this water lift this runner blade towards the tail race, they have to come up with a new design that is known as a draft tube, where the designing of the draft tube has been done in such a way that the tube of the area keep on increasing when it moves towards the downward direction, so that the water can leave this runner blade smoothly without any restriction. So with this, we will be moving to the first part of the reaction turbine, that is the Francis turbine. And about the components, it is similar to what we have discussed in case of the reaction turbine, so just make sure you just revise it. And they have mentioned like how much amount of heat should be included in case of Francis turbine, the flow rate, and specific speed for this Francis turbine. So just make sure you go through this as well. And now I will be moving to the terms that are used in case of a reaction radial flow turbine. The first one is speed ratio, and if I am not mistaken, I remember mentioning you in the class that in order to not make ourselves puzzle, we will be using this denotation for the speed ratio. And before we got this formula, let's talk about this. The speed ratio is basically given by the runner speed divided by theoretical jet ratio. So if you talk about the runner speed, they have taken it as u1, right? Which means, just let's move to the concept of the impact of jet on a moving plate. So in that case, the restriction that is offered to the moving plate, it's given by u, right? So that's the runner speed. They have taken it as a runner speed. And about the theoretical jet ratio, it can be determined using 2gh, and we have been discussing this formula starting from chapter 4, I guess, when we discuss about the orifice. So we have to just take this formula. And about the flow ratio, similar to what we have done for like speed ratio, let's represent this flow ratio by kW2. So we will get this flow ratio by determining the actual velocity flow and then theoretical velocity. And actual velocity can be taken as vf1, and the theoretical can be 2gh. So that is for the flow ratio. And now moving to the third one, that is discharge of turbine, right? So for this case, we will be determining, I will do the derivation here. So basically, we know that discharge is area times the velocity. And when we talk about casing of this Francis turbine and all, and this, if you just go through this, we can see that this is in a circular cross section, and you can see actually it's reflected here. So if we just try to determine the diameter, the width, and all, so we can say that basically, like, to determine the area of this Francis turbine, we can determine the circumference of this inlet, so it can be taken as pi d1, right? And we will be measuring the width as well, which will be taken as b. So it is, if it is d1, then we will be taking it as a b1. So we can get the area by multiplying the circumference d1 times the b1. So this is the area1. So if we just substitute in case of discharge formula, then we will be getting d1 p1. And so for now we were determining the flow of the velocity, then we can take it as a vf1, and that's how we got this equation. So if you want to determine it for, this is for the discharge at inlet part, and if you want to determine the discharge at outlet part, then we can take it as d2 p2 and vf2, and that's how we are getting this equation. The next one is we will be talking about the heat on the turbine, how we got this formula, and then to the final how we reach out to this formula. So for that we will be considering like energy lost from the water will be equal to energy gained by the runner, right? So about the energy loss from the water, we will be taking only the heat. And about the energy gained by the water, it can be in the form of power or it can be in the form of work done. So basically we have got that work done per second in terms of per unit weight, so it can be taken as vw1. And I remember introducing this formula in the last class, so I think you can just revisit it if you are not being able to remember. And along with this work, there will be some kind of energy which may not have been converted into the work. And in case of Pelton turbine, I remember mentioning that the amount of water that has been taken out from the nozzle will be taken as the kinetic energy, and after passing through the runner as well, similar to that of the Pelton turbine, in case of reaction turbine as well, there will be some kind of kinetic energy that is not fully converted into work. So we will be taking this into consideration. So if you just take this formula on the left hand side, that means heat minus v2 squared divided by 2g, then we will be getting the equation that is written in that is represented here. And about this, like the wheel, the tangent on the wheel and all the components of the wire velocity is becoming zero and all, we will be discussing in detail when we solve this question.